Hey folks, today's topic is the real numbers, the real number system, and some of the properties of real numbers. So just like you do in science class, you know how they in biology they have classifications of animals, species and I think genus and kingdoms and all that stuff. Well, we have the same system when it comes to numbers. So there's lots of actually there's lots of number systems beyond this one. I didn't learn about them until I was in college, so you don't have to worry about them probably until then. But the set that we usually think of is the real numbers. Now each set has its own symbol. So the symbol for real numbers is this like fancy R. Now if you don't want to write the fancy, I drew two lines and then drew an R. If you don't want to do the fancy and just want to write R, I'm fine with that. Okay, so the real numbers. Now the real numbers, any number that you can think of is a real number. Probably you might remember from algebra. Oh no, algebra 1. We didn't cover imaginary numbers. So there's another set of numbers called imaginary numbers that we'll get to later on this year. But the real numbers, any number that you can think of, is a real number. The real numbers are split into two categories. They are the irrational numbers. Let me get a different color for that. What would be a good color? The irrational numbers. The irrational numbers, they don't have a very interesting symbol. I just use IRR, or I think the answer key uses an I to represent irrational numbers. And then the other group is called the rational numbers, and they use the letter Q. Makes total sense, right? I don't know why they use the letter Q. I'm sure it's like, maybe rational in German starts with a Q, but they use the letter Q, fancy Q. If you want to just write regular Q, I'm okay with that. So what's the difference between an irrational number and a rational number? Well, let's read. Irrational numbers, numbers in which the decimal form, so I'm going to highlight that, numbers in which the decimal form never terminate or repeat. So it doesn't terminate or it doesn't repeat. For instance, let's take the number square root 3. If you take square root 3 and type it into your calculator, there's no pattern that you can see. Off of here, square root 3, there's no pattern there, right? It does kind of look like maybe there's a pattern at the end, but you could not tell me what the next number is. The most famous irrational number, of course, is pi. Number that never stops, never repeats. There's E is another one that we'll talk about this year. Pretty much any not nice square root and no perfect squares is going to be an irrational number, the square root of 7. Now that's different than, let's say, the square root of 9. Does that terminate or repeat? Yeah, it stops, right? It's 3, boom, 3.0, it's done, it stops, it terminates. That's what I mean by terminate. Let's take like the fraction 1/3. It repeats. See how it's 0.33333? Those are not irrational numbers. Irrational numbers are the numbers that you probably are not thinking of when you think of numbers. They're the numbers that kind of ones that we don't use a whole heck of a lot. It turns out that there's actually more of these than the ones that we do use a lot, but that's the difference. Okay, so those are irrational numbers. Then we have the other half of the real numbers. They're either irrationals or there's rationals. Now, the rationals then break into more groups, and we're going to talk about those in a second. But I want to highlight here again, rational numbers are numbers in which the decimal form, so when you turn them into a decimal, they either terminate or repeat. And I'm going to say above that either, I'm going to actually write does, because the decimal form, I think does makes more sense. Does terminate or does repeat. Rational numbers can also always be written as a fraction of two integers. And if you don't know what an integer is, we're going to talk about those down here. Okay, so when I look at the decimal, is it a decimal that goes on and on and on but doesn't repeat? Then that's an irrational number. Is it a number that goes on and on and on like pi that doesn't repeat? That's an irrational number. Is it a number that goes on and on but does repeat, like that 1/3 that I showed you up above? We typed in 1/3, or square root of 9. Those are numbers that do repeat. Okay, then within the group of rational numbers, there's another set of three types of numbers, and all of these are the ones that have no, I wish I would have done this on the other side. Yeah, I wish I would have done this over here. These have no decimals. So if you're a decimal number, you cannot fit into one of these groups. These are all non-decimal numbers. The first group, I'm actually going to start at the bottom. I don't know why she ordered it this way. I would have ordered the natural numbers are the first ones. These are also called the counting numbers because it's the numbers that you count with. If I'm going to count how many markers I have on my desk right now, what's the first thing I'm going to say? 1, then 2, then 3, then 4, then 5, then 6, go on forever. The natural numbers, their symbol is N. Fancy N if you want to, or just N. So what's the difference between the natural numbers or the counting numbers and the whole numbers? Well, if you look, the only thing we've done in the world of whole numbers is add the number 0. So now we've added the number 0 to the mix. So instead of starting at 1, it starts at 0 and then goes 1, 2, 3, 4, 5, blah, blah, blah. The symbol for whole numbers is fancy W, or just W. That's a pretty crappy W, sorry. And then integers. Integers are the exact same as the whole numbers, except you've got your negatives in there. So these don't have 0. These don't have negatives. These are everything that besides the decimals. And for some reason, and I think it's like a German word or something for integer, we use the letter Z for integers. So what I want to do now is I want to talk about, let's fill out this set first. So the irrational numbers, let's have you pause. I would like you to try to pause here, fill in what letter represents each one of these, and give me what you think are some examples of those numbers. So pause, give it a try. All right, let's see how you did. So the irrational numbers, I'm going to use IRR. You could also use I, but I'm going to use IRR. Okay, some irrational numbers. What's an example of an irrational number? Square root 6 is irrational. Square root 72 is irrational. E is irrational. What about 137 divided by 42? 137 divided by 42 looks irrational, but remember that you could also say that if you are a fraction of two nice numbers, if you're a fraction of integers, remember the integers are just the kind of the nice numbers with their negatives, you are rational. So no, this is not fitting into that category. Even though it's got a weird looking decimal, somewhere this decimal repeats. And if we went far enough, actually, I'm curious. Let's see I'm going to type that into the calculator and see how long of a decimal we can, or into the computer. Let's see how far of a decimal we can get. So I did what? 137 divided by 42. How long can we get it to go? Yeah. I wanted to see, I was hoping that it'd be some really long number, but it's not. Doesn't look like I can find a program that'll do that for us. But you have to trust me that it is an irrational number. Okay, so next, our symbol for rationals. That's the letter fancy Q. A rational number can be a fraction of two numbers, or it can be a decimal that stops or repeats. So like, for instance, 0.324 with that repeating bar over it. Remember that from middle school? That's an example of a repeating decimal. I don't know, 2 3/4. There's an example of a rational number. The number 3 is a rational number. The number 137 over 42 that I referenced up above, that's a rational number. So these are all kind of the nice numbers that you think of. that are decimals. Integers are positive and negatives with no decimals. So -4, -9, 11, 22 over 2, right? Because what's 22 divided by 2? That makes the number 11. This is an integer because it can be cleaned up. What about the number 137 over 40? 137 over 42? That does not fit in this group because when I do 137 over 42, I do not get a nice decimal. I get a messy decimal. So this is still a quotient or rational number, but it's not an integer number. Okay, whole numbers. That's fancy W. Okay, what can't you have here? No decimals, no negatives. So what is a number? I kind of like that I just did that. I'm going to go back and do that up above. So in integers, no decimals. Yes, negatives. So you can have negatives in there, but you can't have decimals. In rationals, you can have positives, negatives, whatever you want. Okay, so whole numbers. What is an example of a whole number? 3. What's an example of a whole number? 0. That's the big one. That's the one that's different between this one and the one below it. How about 20? I just did 22. Let's go 14 divided by 7. What's 14 divided by 7? Does that come out nice? Yes. What about 14 divided by 3? 14 divided by 3, 4.6. Now, it repeats, so this is a rational number, but it is not a whole number because it's a decimal. Remember, you can't have any decimals. 14 divided by 7 is not a decimal. And then our last one, we're talking about the naturals. This is fancy N. This would be no decimals, no negatives, and then also no 0. So 14 over 7 would work again. 3 would work again. Square root of 9. Why is square root 9 legal? It's a square root. That usually goes in irrationals, but what is the square root of 9? Square root of 9 is 3. Does that make sense? What do you think? What do you think? What's 147? No, let's go 48 divided by 6. 48 divided by 6 is the number 8. That number is natural. Okay, so this is kind of an organizational chart. I don't know if this helps or not. It's a Venn diagram. I'll explain it to you, and you can use it if you like. If you just understand from over here how they all fit together, that makes sense to me too. But this Venn diagram is sort of breaking it down from the perspective of how grouping works. So, like, let's take, I forgot to extend this thing, sorry. Let's take a look at, like, let's try to make a Venn diagram for me. So, here's the set of all humans. So this thing right here represents, this piece of paper represents all humans fit on this paper. Within this set of human beings, there's the set of all teachers. Okay, I'm in this group. I'm in this set. Over here, who would be over here? Let's say, I don't know, LeBron James is over here. He's not a teacher. He's a human, but he's not a teacher. You know, my mom is in here. Hey, Mom. My mom is in this group. She's a human, but she's not a teacher. All right, now let's focus on within this group of teachers, there's another group. In this group, these are FHS teachers. So who would be over here? I don't know, some teacher at Mona Shores, some teacher from Spring Lake, some teacher from Reese Buffer. All right, so these are still all teachers, but within that group of teachers, there's the teachers of all the FHS teachers. Within all the FHS teachers, there's another group. These are the math teachers. So let's say, I don't know, Miss Jacobs is in this group. Miss Jacobs is in here. Miss Andre, thinking of my neighbors here in my hallway. Mr. Swanee. Swanee he's in this group, but he's not in with me in the math teachers. And then within the math teachers, finally, there's me. I made it really small. You can probably barely see it. I wish I would have done better, but this is what we got. Who else would be in here? This would be like Mr. Wojo would be in here. Mrs. Murphy, Mrs. Musio, Mrs. Robbins, Mr. Moore. All those teachers are in the group of math teachers at FHS that are also human beings, but this set also just has me in that spot. So that's how a Venn diagram works. So what I want you to do is start here. This set, pause it. This is the set of real numbers. So this piece of paper is all the real numbers. See if you can fill in how this works. Okay, so hopefully you paused it and gave it a try. Oops. All right, so let's see here. So we've got the whole set of real numbers. Those are broken into two categories. There's either the irrationals, and I don't know why they made a little circle here. This circle shouldn't be here. This space around this should be all the irrational numbers, but this is what it is. Okay, and then the rational numbers are the other set. So you're either irrational or you're rational. Within the set of rationals, there's the set of integers. Within the set of integers, there's the whole numbers. Within the set of whole numbers, there's the natural numbers. So, for instance, the number 3 can belong, like the number 3 belongs to all of these rational numbers. But the number -3 does not. -3 would only live in this portion where, see how when I write 3 here, 3 is in this circle, 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 3 is in the real number rectangle, so 3 belongs to all those. I hope that makes sense. If you still have some questions, we can work on it on one of the days that you're in class. Okay, so name the set name all sets to which each value belongs. So I'm talking about you can belong to more than one thing. So -10. First of all, decide, is it real? Yes, everything is real. All of these numbers are going to end up being real. Okay, so after the real numbers, you decide, is it going to break into one of these two groups? Is it going to be rational or irrational? Well, does -10 terminate or repeat? Yeah, it stops. It's just -10. There's no decimal that goes on forever. So this is a rational as well. Okay, is it an integer? Yes, it can have a negatives, but it can't have a decimal. So there's no decimal, but there is a negative, so that can also be an integer. Can it be a whole number? No decimal, no negative. Nope, that's negative, so that's out. And actually, when you get here and you figure out that this doesn't work, then this one won't work either. But if you look, that also says no negatives. So that's a negative, doesn't belong. Okay, square root of 30. I'm guessing you probably don't know what square root of 30 is off of your head, but hopefully you know that 30 is not a perfect square. And whenever the number that you're square rooting is not a perfect square, it's automatically irrational. So, like before, everything is real, and then it's irrational. And once you figured out that it's irrational, you can stop, because these other ones, these 3, all belong within the circle of the rational numbers. 1 7/9. Okay, let's see. 1 7/9. Is that, first of all, it's a real. I guess we can get that one out of the way. 1 7/9. Let's see how we would do that. We would do 1 plus 7/9. That's 1.77778. So does this decimal terminate or repeat? Now wait, it goes 77778 though. Why is that 8 there? Hopefully you know, because it got rounded up by the 7. That's the calculator chops it off and rounds the last number. So there's a 777. This should really be 1.77777 going forever. So is that, when it's a decimal, does it terminate, or does it terminate or repeat, or does it not terminate or not repeat? That repeats. So that means that it's a rational number. Once it's a rational number, then we got to go through the rest of this list. Does it have a negative? No. It could have a negative, it could not. Negatives are okay here, but you're not allowed to have any decimals. So this was 1 point blah, 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 blah. So this is not an integer. Game over. You can stop. Let's have you try the next one on your own. Pause. Try to do it on your own. All right, let's see how you did. First of all, everything's a real, so I can just get that over with. Now, 24 divided by 8, can you clean that up? 24 divided by 8 is the number 3. Oh boy, so this is going to be a lot of things. Does this terminate or repeat? Yay or nay? Yeah, it terminates, it stops, it's 3. So this is a rational. Is it positive or negative? Yeah, it's positive. Are there no decimals? Yes, so that's okay. It fits into ration or integers. No decimal, no negative. No decimal, no negative. So it's a whole number. No decimal, no negative, and it's not 0. Yeah, that falls into all of them. So that's everybody. That fits everything. Pause and try the next one again. 2.48. It's a real. As a decimal, does it terminate? Yes. So it's a quotient. It's a rational. Does it have a decimal? Yeah. So if it has a decimal, then it can't be in here because integers mean no decimals. So that's it. Game over. It's just R and Q. Negative square root 81. Can you clean it up? Yeah. Square root of 81 is negative 9. So you can clean that up. So let's go through the list again. I forgot to change colors. So we got reals automatically. Okay, is it rational? Does it terminate or not terminate? Does this go on forever as a decimal? No, it doesn't. It stops. So we can put it into quotients. Dang it, quotients. You can put it into rationals. Within rationals, integers are allowed to have negatives. They don't have to be negatives, but they're allowed to have a negative. So that's okay, but you're not allowed to have a decimal. That's okay. So this fits with that group. Whole numbers, no decimals. Good. No decimal. No negatives, though. Okay, so that's out. So game over. That's it. Rationals. Sorry, reals, rationals, and integers. Pi minus pi, can you clean it up? Yeah, pi minus pi is 0. Pause. Try it. Let's see how you did. 0 is a real. 0 terminates, so it's a rational. 0 is not a decimal, so it fits in with the integers. 0 is not a decimal, nor is it negative, so it fits in with the wholes. 0 is not a decimal. Nope, naturals do not include 0, so that's it. They don't include naturals on that one. Oh boy, let's see if we can clean this up. Is the square is first of all, can 16 and 25 be cleaned up? No. But we can square root 16 and 25. The square root of 16 is 4. The square root of 25 is 5. So it's a real. Okay, is it a quotient or is it an irrational? If you take 4/5, does it turn into a decimal that terminates? Yes. So that's a quotient. Or sorry, rational. That's a rational. I keep saying quotient. So it's a rational. Now let's go through our list. Is it an integer? No, it's not. Because look, integers, you're not allowed no decimals here. So no on being a decimal. This is a decimal. So game over. It's just rationals and reals. 0.15. Pause it. I'm gonna just keep going, but you should pause it after each one of these that we do together and try it on your own. It's a real. As a decimal, does it? I kind of like writing that in here. That equals 0.2. I kind of like writing that. I'm going to go back a little bit here, folks. This is 1.7 repeating. Okay, so down here they gave us it's 0.15 repeating. So as a decimal, that repeats. So if it repeats, then you're rational. But it is a decimal, which means all three of these, none of these can have decimals in them, so that doesn't belong to any of those. Keep putting that comma in there. I wish I wouldn't do that. And our last row, 109, that's real. That's a decimal that stops because it's 109.0. It stops, so that's a rational. It doesn't have a decimal, and it doesn't have to be negative to be an integer. It doesn't have a decimal, nor is it negative, so it's also a whole number. And it's a number that's not 0, so that's a natural. Negative 8/3. Let's see what negative 8/3 is on the old calculator. Negative 8/3. Negative 2.6. Now, is this repeating or not? Yes, that's repeating. Don't get caught by that number at the end. Negative 2.6 repeating. So it's automatically a real. Does it terminate or repeat? Yes. So that means it's a rational. And then the bottom three, this is easy. Those three can't have decimals. That's a decimal. Game over. It's just those two. You try the last one. Ooh, root 7. Root 7 is not a pretty number. That's not one. So that kind of feels like it's irrational, but this is root 7 divided by root 7. So root 7 divided by, oops, I forgot to put the 7 in there. Root 7 divided by root 7 is 1. This is equal to 1. Anything divided by itself is automatically 1. So 1 is a real number. 1 terminates as a decimal, so that's a rational number. 1 doesn't have a decimal, so that's an integer. 1 fits in with the whole numbers. It's not a decimal, nor is it negative, so it's a whole number. 1 is not 0, so it's a natural, so everybody's on that list. Okay, I think I'm just going to keep going here, and we'll get through the rest of these notes, and hopefully the back is going to be fairly quick. So we've got these properties, the commutative, associative, identity, inverse, and distributive. I want to talk about them kind of in normal terms and see if it makes sense. All right, so here, think about it, what I mean by normal terms. I'm going to try to give a real life example. So person A and person B are talking to each other. What's another word for talking to each other? Communicate. So that's how I remember commutative is like communicating. If you have two people communicating to each other, does it matter if person A starts to talk first or if person B starts to talk first? No, it doesn't matter. So commutative property means as long as we're talking to each other, it doesn't matter if we look at it from your point of view as being A and me being B, or if we look at it from my point of view of being B and A. This makes sense with numbers. I mean, put 3 and 10 in there. What's 3 plus 10? 13. Now flip those numbers around. What's 10 plus 3? 13. You get the same result. Now for addition and multiplication, they both live up to the commutative property. A times B and B times A. Associative. Now this one's a little tricky. How do you remember which one's associative? You've got 3 people talking in an associative situation. In the first case, who's talking together? Person A and person B are talking to each other. In the second scenario, person B is talking to person C. Are we all having the same conversation? No. These are 2 different scenarios. So when I think of associative, I think of who am I associating with? In here, A is associating with B, where here B is associating with C. Now, I'm going to still have the same conversation. So let's say the letter B is Miss Chesney. If she comes talk to me first and has a conversation about what we're doing on a delayed start Wednesday, and then she goes and talks to Mr. Wojo, what's the difference is if she talks to Mr. Wojo first and then tells me about it, she's still going to tell us the same stuff. And that works the same when you start to put some numbers in there. The associative property also works for multiplication. So when I associate A and B first, and then I associate B and C first, as long as they get associated with the other term, you're going to get the exact same result. You're going to get the exact same answer. Okay, the identity. If you keep your identity, does anything change? No, obviously not. And that's what the identity means. In the world of addition, what number can you add and A keeps its identity? So if this is you, how much would you add to you to stay exactly the same? You would add nothing. You would add 0. In the world of multiplication, what would you multiply by to leave you exactly the same. 1. These have a special name. This is called the additive maybe I can zoom in a little bit. Additive identity. 0 is called the additive identity. 1 is called the multiplicative identity. I think I made that an M. Identity. There we go. 1 is the multiplicative identity. So those numbers don't change anything in the world that you're talking about. What I mean by that is in the world of addition, 0 isn't going to change anything. In the world of multiplication, what's 0 going to do? Why isn't 0 also the multiplicative identity? Well, if I take the number 7 and I times it by 0, let's start here. If I take the number 7 and I add 0, what do I get? 7. 7 keeps its identity. If I take the number 7 and I multiply it by 0, it would kill it. It would not make it, it would not leave it as 7. So 0 is only the additive identity. 1 is only the multiplicative identity because 1 doesn't change anything in multiplication, but it does change things in addition. Inverse. I always think of inverse as reverse in terms of like canceling things out. So who would cancel out A? Who would cancel out the number 3 when you add? 3 plus what would end up giving you nothing? Well, it would be negative A or negative 3. Like 3 plus negative 3 is 0. That's what we mean when we're talking about an inverse. This works in the world of multiplication, but it's a little more complicated. If I take the number 3 and I multiply it by 1/3, I would get 1. And then the last one is the distributive property. You guys usually know this one. If I take A times the quantity B plus C, when I distribute that, I would get A times B plus A times C. All right, let's kind of go through and see which property each one of these are. So if I'm looking at this first one, if you think you're ready, maybe you try this on your own. Okay, in this case, 2 is getting associated with 8, and then it's going to 5 because of the order of operations. 5 is associated with 2, and then it's going with 8. So I'm associating different things. This is the associative property. And because those are all dots, this is the world of multiplication. All right, 3 is getting associated with 7, but over here there are no parentheses. So what happened to those parentheses? Oh yeah, we took this and we distributed. I took this 6, I gave it to the 3, I took this 6, I gave it to this 7. This is the distributive property. And you don't have to write multiplication after that. We know that distributive only works in the world of multiplication. All right, we took something, we added the opposite something and ended up with nothing. So we reversed it. We took 7 and we reversed it so that there was nothing left. So reverse is how I remember inverse. Now, which kind of world is this? This is addition. I'm going to be happy if you can just write that down. You don't have to write that down if you don't want to. All right, let's see. What do we got next? We've got 3a plus 2b is this. Okay, so 3a and 2b are talking to each other. Does it matter if 3a talks first or if 2b talks first, or are they still having the same conversation? It doesn't matter. They are communicating the same. You're still going to have the same communication. So this is the commutative property. Commutative property with addition. All right, I'm going to have you pause here and try to do these last 4 on your own. All right, let's see how you did. So x squared is talking to 8x and then talking to 1. Where over here, 8x talks to 1 first and then talks to... So this is where they're associating with different people. So that in this case, they associated the first 2 together first and then switched to the second set of people. It's the associative property under addition. Over here we have 1/5. Okay, so these things multiplied together and it ended up with, in the world of multiplication, 1 means nothing. 1 doesn't change anything, so this is like nothing. So I reversed. I took 1/5 and I multiplied it by 5 and reversed it into nothing. For me, reverse means inverse. This is the inverse in the world of multiplication. 3m plus 3n, and then, this one's kind of weird, but keep in mind, how could you take this 1, 3 and give it to both of those inside? The only way to do that is to distribute. So this is the distributive property. And then last but not least, what are we up to here? 9c, you took something, you added nothing, and still got 9c. So we didn't change anything. What happened to 9c? 9c kept its identity. And this one, because it's addition, this is the additive identity. Okay, so let's go back here. Here we've got these identity ideas, the things that undo them. So if I wanted to start with -8, what would I have to add to it to end up with nothing in the world of addition? Well, it'd have to be +8. -8 plus 8 ends up with 0. Now we're in the world of multiplication. This gets a little stickier. You've got to multiply -8 by something, and what should I get as my answer? I should get nothing, quote unquote, the nothing thing in the world of multiplication, which is 1. Well, let's try 1/8. So hopefully you remembered that it's the reciprocal. But that left me with -1. -1 is not the inverse. The identity. So -8 has to get multiplied by -1/8 to end up with the 1 there. So this would be -1/8. Okay, what would I add? Let's have you pause and try to do number 22. All right, what would you add to 2/3 to get the additive identity? In other words, to get 0. I'm going to go back and put that. I kind of like that I have that there. The additive is 0. The multiplicative is 1. Well, I would hopefully you got this one. This one's the easier one of the two, I think. -2/3. Now, what would I multiply 2/3 by to end up with a 1? So 2/3 times -2/3. Oops, I messed that up. 2/3 times -2/3. Nope, that's not 1. So let's try something else. 2/3 times the reciprocal, which is 3/2. Now we get into the idea of things that aren't just nice numbers. When we talk about our rational numbers, these aren't rational numbers. So what's the additive identity of 6w? In other words, what I want to end up with a 0 here, and I want to end up with a 1 here. What could I add to 6w to end up with nothing? That'd be -6w. And what would I multiply 6w by to end up with 1? So if you look up above, what did we do to 8? We made 8 into a fraction and then reciprocaled it. What did we do with 2/3? We reciprocaled it because it already was a fraction. So I'm going to take this, I'm going to make it a fraction, I'm going to reciprocal. What could we do to square root of 10 to make it add to 0 or multiply to make 1? So the additive would be its opposite. The multiplicative, I make it a fraction first, and then I reciprocal it, 1/√10. All right, this phrase, closure. A set is closed under an operation if the operation always produces an element of the same set. If an element outside the set is produced, then the operation is not closed. For instance, let me give you an example here. Let's pick any integer, -3, and I'm going to add another integer, negative 3 plus 7, and I end up with 4. Is that still an integer? Yeah. So that's what I mean by closure. If you take something from that group, you add something from the same group, it's still in that group. So this is closed. So what would the opposite of that be? Well, let's take a look. Let's take the number negative 3, which is an integer. And this time I'm going to add an irrational, square root 10. Negative 3 plus square root of 10. Negative 3 plus square root of 10 ends up being positive 0.162. But what did we say about integers? Integers are not allowed to be decimals. So I took an integer, I added something, and I got something that's not an integer. So this is not closed. Hopefully that makes sense. Don't overthink it. I can put together some examples when you guys come into class. Okay, integers are closed under multiplication. So if you take an integer like negative 6 and you multiply it by another integer like 17, why did I pick that? I don't know. Negative 6 times 17 is negative 102. Negative 102 is still an integer. So that was an integer times an integer. It ended up being another integer. So this is true. Irrational numbers are closed under subtraction. So if I took something like, I don't know, square root of 15, subtract square root of 7. So this would be square root of 15, take away square root of 7. I still get some really weird, crappy number. That's still irrational. Oh, wait. Sorry. I did not pick a very good example. Let's take something easy like pi. What's pi minus pi? 0. So this is an irrational. I subtracted another irrational, but then what did I get out? I got a whole number out. So this is false. Whole numbers are closed under division. Whole numbers are closed under division. So if I take any whole number and I divide it by another whole number, I'll get another whole number. So let's just randomly pick a whole number. Let's take the number 13. Let's take another whole number. Another whole number could be 4. 13 divided by 4, I'll grab my calc. You don't need to see it. 13 divided by 4 is 3.25. Is that still a whole number? Nope. So 13 is a whole number. 4 is a whole number. But when I divided them, we got a decimal that terminates. That's a rational number. So this is also false. And finally, odd numbers are closed under addition. I think this one's probably just easiest to try to pick an example. Like just pick 2 odd numbers. Like then the odd number 7 plus the odd number 3. When I add 7 and 3, do I get another odd number? No. So in this case, an odd plus an odd ends up being an even. This is also false. So the only one that was true was the first one. All right, so that's a lot thrown at you there. Homework is pretty short. It's only 1 page. So give that a try. I'll post the answer key shortly, and you should have that to be able to check your work. All right, take care.